Okay, so next I want to discuss a very useful tool for doing calculation, which is generating functions. So let me discuss this by starting with an example, a very famous one of Fibonacci numbers. Okay, Fibonacci numbers are defined in this way. So f of 0 and f of 1, so the zeroth Fibonacci number and the first one are equal to 1. And for n, the other ones are obtained by summing the previous two. Okay, so for example, you can see that f2 is equal to 2, f3 is equal to 2 plus 1 is 3, but f4 is equal to 5, which is 2 plus 3, etc., etc. Okay, and so on. So the question is, can we estimate Fn for large n? How do we estimate? Of course, you can put this in a computer and run the computer as long as you want and compute this number. But is there a smart way to compute this number? And in particular, maybe we are just interested in understanding how this number behaves as n goes to infinity. Okay, what is the asymptotic behavior of this sequence when n goes to infinity? Okay. So in order to address this question, the idea of a generating function is that for any sequence you can construct a function which is in this case given by this expression. Okay, so you take the coefficients of your sequence, you multiply by s to the power n, and then you sum over all n from 0 to infinity. So what is s? So s is just a computational device. It does not have any particular meaning. It is just used as a tool to do calculations. Okay? So, what is the idea? Well, the idea here is that if you take this recursion relation, you multiply by s to the n plus 2, and you sum over all, and then you sum over all n which are positive, which is where this rule applies. Then what do you get? Well, you get on this side you will get so you multiply by ns to the n plus 1. So on this side you get this exactly this series minus the first two terms, which are 1 and s. So you get f of s minus 1 minus s. On this side, when you multiply by s to the n plus 1, s to the n times this gives you f of s minus 1, because in the series, in the sum, you don't have the first term. And then you have the plus 1, which gives you an s. And when you multiply these to these and sum over all n, instead you get s squared times f of s. Okay? But it is very nice because you can derive from this by simple algebra an explicit expression for the generating function f of s. Okay? And what is more interesting is that you can write this, you can expand this expression in simple pole. You see that this is with s as a complex variable. This is an analytic function that has two poles at the roots of this quadratic equation. So, and in general, so it can be written as, so if you do the calculation and compute these two poles, then what you see is that this can be written as minus 1 divided by phi plus s, where phi is the golden mean. Okay? So this, now, the important point of this is that both these two terms can be expanded in powers because they are just geometric series. Okay? So essentially, from this you can get that f of s is equal to 1. So this, say for example, this one is just phi times some n goes from 0 to infinity of phi times s to the power n. Now, if I also consider the power expansion of this and put the term s to the n as a factor, then I can write f of n in this form. 5 times phi to the n plus 1 minus 1 over phi minus 1 over phi to the n plus 1 times s to the n. So, and now you see, if you look at this expression, then you can see that this is exactly equal to f of n. Okay? So you can get an explicit expression for f of n for any large value of n without having to do this calculation. What is also remarkable is, in this particular case, is that you see phi is an irrational number, but this particular combination for every value of n produces a number which is an integer. Okay, and this is well, a special property of, say, these irrational numbers. So the other thing is, now if you want to understand how, what is the behavior of f of n as n grows large, then you see that f of n is the sum of these two terms, but this phi, the value of this phi is larger than 1, is 1.61803, etc., etc. So, because this is larger than 1, then this is larger than 1 over phi. So when n is larger, this term will be exponentially larger than these other terms. So this term can be neglected. So the asymptotic behavior of f of n is essentially given by 1 over square root 5 times phi times phi to the n. So it's an exponential behavior, so it's of the proportional to e to the alpha times n, where this alpha is just equal to the log of phi. Okay, so these numbers grow exponentially, and we can compute the rate of exponential growth. So now if you look at carefully at what we have done, we have seen that the asymptotic behavior for n going to infinity is related to the singularities of the generating function. In particular, if you think carefully, it is related to one of the two singularities, which is the singularity at 1 over phi. Okay? Here there is another singularity which is at minus phi. So it is related only to the singularity which is closest to the origin in the complex plane. So if this is the complex plane of S, this is real of S, and this is imaginary of S. Then here there are two simple poles in this function. One is at minus phi, and the other one is at 1 over phi. Okay, and it is this singularity here that only determines the leading asymptotic behavior. So what we are going to do next is to show that this is actually true in general. So let me state the problem that we are going to discuss. So we are interested in a particular sequence then we are interested in its asymptotic behavior. So the question is how is AN behaving asymptotically? For n going to infinity. And in particular, so for example, if AN is a behaves as a constant times say a constant times n to the beta times n e to the minus alpha e to the alpha times n. So we want to compute what is beta and what is alpha. Okay. And the idea to answer this question is to build the generating function. So we define AOS as this is is the generating function. This is the generating function of the sequence AN. And what we want to show is that if we want to answer this question, what we can do is to build this function here, study the structure of the singularities of this function, and then read from the nature of these singularities what is the asymptotic behavior. Okay? So let me start with the simplest case. So the simplest case is the one like the one of Fibonacci numbers that we have discussed before, where the generating function is just the ratio of two polynomials. Okay, where so the polynomial, so these two are polynomials, and the degree of D, let's call it D, is larger than or equal to the degree of N. Okay, so if you are not in this case, then so if the degree of N is larger than the degree of S, you can easily reduce to this case by just dividing the two polynomials. Okay. Okay. So if this is a polynomial, then it means that it has D roots. Okay. So the equation E of S equal to 0 has a number of solution which is exactly equal to D. Okay, these are the zeros of D. And let's start by assuming that all SI are different. Which means that essentially this function has D simple poles. Okay? These simple poles, and we know that they are either real or in complex conjugate pairs. Very good. So, okay. So if this is true, then it is possible to write again to expand this fraction of two polynomials into simple into a sum of single poles. So what is the idea? So the idea is that essentially if you expand this object here, it will again be so if you take you can reduce this to this by just taking the common denominator, and you will see that at the denominator you have exactly a polynomial of degree D with exactly the same roots. So this is so what you have at the denominator is exactly proportional to this polynomial here, and at the numerator you will have another polynomial, and you can choose these numbers rho I in such a way that this polynomial is exactly equal to n of s. Okay, The only way to compute these numbers rho I is to impose that if you take the limit as s goes to si of this object here times s minus si, then you should obtain the same. So if you multiply this by s minus si and this by s minus si, you take the limit as s goes to si of these two things, you should get the same result. Okay, and in this case, this gives you exactly rho I, because all the other terms will vanish because all the roots are different. So this is so rho I is the limit as s goes to si of essentially n of s divided by d of s. Now, as s goes to si, I can use the say L'Hopital's rule to compute this. So it wants an explicit expression. So this is the limit as s goes to si of n of si actually. So this is without the limit. So because so the derivative of this is 1 and the derivative of this is d prime computed in S1. Okay. Okay, so now once you have this function written in this way, then you can just expand this in geometric series. You can just use the geometric series and rearrange a little bit take s to the n factor it out. So what you will get is minus sum over I from 1 to d. So you write this as minus 1 minus s over si divided by si. So you have rho I times si to the minus n minus 1 times s to the n. Okay? So you see that here is your coefficient an. And now you can see that so so in this case the coefficient an is just given by minus somewhere I from 1 to n d of rho I divided by si to minus n. Okay? Now, again, in the complex plane of S, so you have these different poles, okay, so, and now what you see is that this an will be dominated by the pole, by the zero of d of s, by the singularity which is closest to the origin, okay? Because the contribution given by the other poles will give you an exponentially strong, exponentially smaller contribution. So if we assume for simplicity that say S1 is less than S2, etc., etc., then we'll say that the modulus of, so that this is S1 is the closest to the origin, Then from this you see that the asymptotic behavior is given by the root which is closest to the origin. Rho 1 divided by S1 times S1 to the minus n. So this tells you that so if you want to compute this number here, so this is so this alpha is given by the log of of minus the log. So alpha is given by minus the log of the modulus of the closest singularity to the origin. Okay, so the location of the closest singularity gives you the exponential rate. So the closest is to the origin, the faster it will be the growth. Okay, so so now if we want to get more details, then we have to look at different more complicated cases. So let's say, for example, the case where this pole is not a single pole but a double pole. So ARS is equal to, say, rho 1 divided by S minus S1 squared plus something else. So this is clearly easily reduced to this one, because this is just minus the derivative with respect to S of rho 1 divided by S minus S1. And so you see that if you take so essentially the case of a double pole is exactly the behavior that we expect, is just the one that we expect from the derivative with respect to S of this case here. But we have seen that the leading behavior of this series was this times S to the n. So when I take the derivative with respect to S, what I get is that the leading behavior of an becomes proportional to what it was before, e to the alpha times n times a factor of n, because I've taken a derivative with respect to S. Okay, so the prefactor, the sub-exponential behavior, the sub-leading behavior, is given by the nature of the singularity. So whether it's a single pole, a double pole, etc. So, and in general, we can understand this more precisely if we consider another example, which is a generating function where which is of the form S1 minus S to the minus say beta minus 1. Okay. So what is the leading behavior of the, what is the asymptotic behavior of A of n in this case? So, well, this is easily seen because we can use the binomial expansion. So this is from 0 to infinity of minus beta minus 1, choose n of say S1 minus beta minus 1 minus n times S to the n. Okay? So from this you immediately read what an is. So an is just this just S1 the minus beta minus 1 minus n. Again, you see that the exponential behavior, the leading exponential behavior, will be related to the closest singularity to the origin. And then you have this binomial coefficient. So let me expand this as usual by minus beta minus 1 minus beta minus 2 etc. etc. minus beta minus n, and this is divided by n factorial. Okay, so this is just the definition of the binomial coefficient. So here I can take a factor minus 1 to the n, sorry, and this is minus s to the n, no? Because this is minus s, okay? So I can take a factor, this is a factor minus 1 to the n. So I can take this factor minus 1 to the n and change all these signs, and so I get beta plus 1 times beta plus 2 up to beta plus n. So if I multiply this by gamma of beta, if I multiply by gamma of beta plus 1 above and below, this gamma beta plus 1 times beta plus 1 gives me gamma of beta plus 2, and this gives me gamma of beta plus 3, etc., etc., up to gamma of beta plus n. So gamma of beta plus n plus 1 divided by n factorial. Okay. Now, if I want to compute the asymptotic behavior, I can use Stirling formula. And I give you this as an exercise. Oh, sorry, and there is a gamma of beta plus 1 at the denominator because I'm multiplying both above and below. So I give you this as an exercise, but essentially what you get is a coefficient which is s to the minus beta minus 1, s1 divided by gamma of beta plus 1, n times n to the beta times s1 to the minus n. Okay, so you see that the nature of the singularity essentially determines the subleading behavior of the coefficients when n goes to infinity. And so indeed this thing, this relation between the nature of the singularity and the subleading behavior has been generalized actually for in a very very general type of singularity. So there is a theorem by Flageolet and Odilsko that says that if ARS is a function, if you have a generating function which is a function of 1 over 1 minus s, Here I'm just setting S1 equal to 1 for convenience, where f of u as a function of u as an asymptotic behavior, which is given by u to the beta times log u to the gamma times log u to the delta. Then the associated sequence has a behavior asymptotic when n goes to infinity, which is given by 1 over gamma of beta times this same function f of n divided by n. Okay, so for n goes to infinity, in the sense that if you take an divided by this and you take the limit as n goes to infinity, you get 1. Okay? So, summarizing, you have two principles that one could call the first principle of coefficient asymptotics that tells you that alpha is given by the location of the closest singularity and the second principle of coefficient asymptotic that beta is given by the nature of the singularity, that is, what is the specific analytic behavior of the generating function close to the singularity. Of course, in this lecture, what I've shown is how do you go from a generating function to the asymptotic behavior of the sequence by showing you specific examples where you can get an explicit expression for A of n. But this theorem tells you that this will be true for any general sequence, even if you don't know the explicit expression.